recording the session. Okay, so most of the students are saying good. This was a different experience, but good. Many students are also saying this one. Some students are not saying not good. Okay, some students are, 4 students have not replied. Please reply. Okay, Aditi Thakur has not replied. Please reply. Yes, I think most of the students have replied, except one student. Let me find out the name of the student. Simranjit Kaur has not replied. Simranjit Kaur has not replied. I would like to share these responses with you, that what is the thinking of the students. So yeah, I'm sharing these results with you. Okay, so okay, so yeah, we would have the second poll which we would like to have. So with the help of the second poll, we would like to know that if result of MST. MST. Yes. No. Yes. We got result of all MST. Yes or no? Not yet. I think it should be simultaneous. I mean that. Okay. So there is no result. Okay. Right now. Okay. No problem. Yes. Okay. Let me have another quick poll. What was topic of I'm just putting some options. Okay, let's have a quick look at these options. What was our topic of discussion in last lecture? Okay, good, good. Yes, cool. Yes, hurry up. So we have most of the responses. XRD 41. Okay, so we have. Okay, quickly, can you reply? Rest of the students, can you reply? Okay, let me share the responses with you. Okay, I'm sharing the responses with you. So you have 36 students are saying LEED and the 16 students are saying XRD. So 16 students, please note down that it was with the majority of the students, it was LEED, the topic. We have started the unit 2, and in this unit, we would like to have the information about what's going on in the LEED. Okay, so let's have a quick look what we have done so far. And I would also like to pull up this information for you to see the recordings if we have availability of these this recording from our previous session. So let's have a quick look at it. So yeah, we started with this unit number 2, and what we have done that we try to understand the electron diffraction in a different scenario. Okay, so now what we are trying to do that this electron diffraction which you have, you can use this electron diffraction to probe the surface of the samples. And how we are going to probe this surface of the sample? Again, the basic principle remains same, that you have a sample, and what you are trying to do, the beam of the electron is going to hit the sample. And once that beam of the electron hitting the sample, in that case, what will happen? You would have different type of scattering processes which are going on there. So you would have the electron which are emitted from the surface of the sample in this case. So now you have to understand that what you would have, number one, there will be many scattering. There may be emission of the electrons, but our main aim in this case is not the emission of the electron, but it is the electrons which are responsible for the constructive interference when they are the sample is being um, exposed to the primary radiations. Okay, so that would be our main aim in this case. That what we are trying to do. You would have electrons which are incident, and we have these electrons which are the incident electrons in this case. No? So how these incident electrons are going to interact with the material, with the surface of the sample, and how these will be going to scatter. So that we would like to study in this case. No? So that is one of the things which we would like to have the information about. Okay, so let me have a quick look at the lecture which we have delivered. Okay, so let me share my screen with you. So let's have a quick look at share screen. I'm sharing entire screen. So here you have the information which we were looking for, and then we came across this. The voltage which you are applying in this case, that what would be the voltage, typical voltage required for the operation. That was discussion of some of the questions. Okay, so that's before this lecture we were having this information about the, let's pull out that information for you. Okay. The idea was that how we can demonstrate this effect of the incident electron. So let's have a quick look at it. Okay, so what we have done in this case, that if you recall that our the setup, no, in this case, how it was, yeah. So if you look into the details of this setup, then what was our main point in this case? Okay, so this one is the experimental setup. If you recall what we were talking about, you can have additional detection if you require to have. Okay, so what would be the simple setup? That the simple thing which you have, that the electrons, they will be incident from the electron gun, and then they will hit the sample. And the only difference between the LEED and RHEED, which is a reflection high energy electron diffraction, is that the energy of the electron, that is smaller in case of the LEED. Okay, that is 20 to 200 electron volt. So what will happen, that in this case you would have the interaction of the electrons thing which you have that. Okay, so at this point I would like to make it very clear that what is the different instruments in our instrumental or the experimental configuration of the LEED. What are the different parts of that LEED? So first of all, we have an electron gun. As in all of the cases we would have an electron gun. Okay? So what will happen that the electrons which are coming from this electron gun, they will hit the sample. Okay, so main physics remains same, that you have a sample and you are exposing this sample to the incident electrons. So what will happen in this case that here now the scattered electrons which are there, okay, so you would have the scattered electrons from the surface of the sample, they will go back. Okay, so you would have grid number 1 and grid number 2. What was the use of the grid number 1 and grid number 2? Let me, I think if my voice, okay, let me have a quick look at the settings of the session, so that we can have this okay, better voice experience. Okay, so I am just disabling your voice. Okay, so let's come to it again. What we are trying to do, that here we have this the basic principle remains same. You have an electron gun. The electrons will strike onto the surface of the sample, and you know that the energy of these electrons is from 20 to 200 electron volt. So basically these are the low energy electrons, and when they hit the sample, after that what will happen, you would have the scattered electrons, they have to go through grid 1 and grid 2. No? So these are the two grids which we have in this case. Now, what is the purpose of these grids? Okay, the purpose of the grid number 1 is like a spacer between the sample chamber and the detector chamber. Okay? So what you would have, what are the three things which you need to have in case of the detector? Okay, you need to have the important components. Three important components are: number 1 is the electron gun, number 2 is the sample, number 3 is the detector. Okay, so that's the only information which you need to have when you are trying to understand the LEED configuration. So now what will happen, that what is the detector? So if you look into the grid 1, grid 2 and the fluorescent screen, the third grid which you have here, okay, this third grid which you have in terms of the fluorescent screen. So what will happen, that these three grids, they are acting as spacers. Okay, first grid number 1 is a spacer between this the sample 1, this the sample chamber and the detector chamber. Okay, this is the detector chamber. Okay, because here what will happen, the electron will be detected when they will strike onto the surface of the fluorescent screen. Okay, in the second case, what is the role of the second grid? The role of the second grid is to stop the inelastically scattered electrons. Okay. The role of the second grid, grid number 2, is to stop the inelastically scattered electrons. Okay. So what is elastic scattering and what is inelastic scattering? In case of the elastic scattering, both momentum and kinetic energy of the electron, that will remain conserved. Okay. In the case of inelastic scattering, momentum remains conserved, but the kinetic energy does not. Okay. So what will happen in the second case, this grid number 2, that will stop these electrons, and what you will get on the fluorescent screen, so you would have the electrons which are scattered electrons, and after getting these electrons from the surface of the sample, these will be interfering constructively, and when they are interfering constructively, you would have different spots on the surface of this fluorescent screen. When you are having these spots, once you have these spots, this means that, okay, what you are trying to do, basically you are trying to understand the behavior of the electrons which are coming from there. Okay, and you are trying to understand the electron diffraction in this case. No? That the things are very clear, I think, in this case, that what we would like to talk about. No? So that the thing which we have in our mind. Okay, so let's have a quick look what we are talking about. So now one thing is very clear. What we are trying to say that the you have a sample and the electrons, they are hitting the surface of the sample. The story is nothing but it is just they are hitting the surface of the sample. Now when they are scattered from the surface of the sample, they are detected with the help of a detector, which is in terms of a fluorescent screen in this case. So what will happen ultimately, that you have to look that what would be the depth which can be probed with the help of the system which you have in this case. No? So let's have a quick look at this again. So what we are trying to do in this case, so we would have again our, let's have this system. So again we are talking about LEED. Okay, LEED. So that is LEED. And here in this case what we are trying to do, make it a bit thicker. So what we are trying to do in the case of LED, that the full form of LED is the low energy electron diffraction. So we have to take into account that, okay, once the one part is you would have less energy of the incident electron, and this one is that the electrons are diffracted. Okay, so basically you are trying to address the problem of the electron diffraction with the help of this one, this LEED setup. No? So let's have a quick look at the surface sensitivity. Okay? So what we are pointing out, we would like to say something about the surface sensitivity. Okay, so about the surface sensitivity, if I write one formula, so that will give us the information. I is equal to, let me make it a bit bigger. I is equal to I naught, okay, exponential of minus d over lambda, capital lambda. That is the formula which we would like to highlight in this case. So what are the different components in this case? So you would have D is nothing but it is your penetration depth. What is D? It is the penetration depth. Penetration depth. And what is lambda? Lambda is the mean free path. Okay? What it is? It is the mean free path of the electron. Okay? Mean free path of the free path of electron. And what is I? I is the intensity. This I naught is the intensity, incident intensity of the electrons. Okay? Incident intensity of the electron. Intensity of electron beam. Electron beam. Okay. So we would have this information, and then you would have, this is the intensity at let's say that at any penetration depth. Okay, so what it is the, this one is the intensity at penetration depth. Okay? Penetration depth d, okay? At any. Okay, so I would be a function of like id, you know? Penetration depth. So if you look that what is the mean free path of the electron, how do you define it? So it would be the uh, let's say that if the intensity, where the intensity which is incident intensity will reduce to 1 by e times the this intensity. Okay, so let's say that, okay, the the intensity at which the incident intensity reduces to 1 by e times is known as mean free path. Okay, so let's say that what you are trying to do, let's try to make it sure that you have the electrons, they are hitting the sample. Okay, so now what will happen that this one thing we have to make it clear that you have only this knowledge of the surface. We cannot have the knowledge of the entire sample. It will be only the knowledge of the surface of the sample, that what is happening on the surface of the sample and how these electrons, they are going to interact with the help of this one. So let's say that when you have the I naught intensity, when this intensity will decay to 1 by e time, in that case that would be your mean free path in this case. Okay, so basically what is mean free path? Mean free path of one is the uh, the distance traveled, average distance traveled between the two consecutive collisions. Okay, so let's say that, okay, what we are trying to do in this case, that we are trying to do that what are the scattering events which can take place. Okay? So for example, the scattering events which can take place in this case are like, if you are dealing with this, then you can have the let's say that you can have the phonon interaction. You can have phonon interaction. Okay, phonon interaction. You can also have electron phonon interaction, electron phonon interaction, phonon interaction. You can also have electron scattering. Okay, electron interaction you can have in this case. No? So what you would have, you would have various events. Okay, the story is that what else you would have in comparison to what is happening inside the sample apart than your scattered electrons, okay, which are coming, because what your surface, when you are trying to hit the surface, you would have scattered electrons, and these are collected with the help of the hemispherical screen which we have discussed. So what will happen in this case, that hemispherical screen which is there, that that will collect only the scattered electrons which are interfering constructively in this case. Okay, and rest of the electrons, they will be stopped either by the grid 1 or grid 2 in this case. So let's see that. Okay, now so if you look into the formula, the second formula which we are coming across, which is very oftenly, which we are writing h over under root. Okay, so it was 2 me, that was the formula which we were writing. And in this case, okay, if lambda, if you have an estimation of this, then indirectly you would have the under root of E, that is in terms of volts. Okay, so if you are increasing this, you can control the wavelength of the electron if you are controlling the voltage which is given to the filament plus the voltage which is given to the the surface of the sample, in this case how they are attracted towards the sample in this case. No, that would be the main aim, to have the knowledge of this surface. Now let's come to the point that we can write. Let's say that if you have a star, how do you write the reciprocal vectors? Okay, what are the reciprocal vectors? Reciprocal lattice. So if you look at the reciprocal lattice, in that case what you would have, if you are looking at this one, you would have 2 pi b cross c, b cross c, and here you can write a dot a dot b cross c, no? C, and then you would have b star. If you look into this, this is also vector, This is also vector. Okay, so don't forget them. 2 pi, okay, C cross A divided by A, sorry, it would be like your C cross A B dot. And then you have C star. If you are looking into this, then you would have 2 pi A cross B divided by, you would have C dot A cross B. Okay, so these are the reciprocal lattice vectors. Okay. And what is the meaning of the reciprocal lattice? So if you recall, in case of the solid state physics, we talk about two types of the lattice. One is the real lattice and the second one is the reciprocal lattice. What is the meaning of the reciprocal lattice? Basically, when you have this sample, you are hitting the incident electrons, they are hitting the sample, and then you would, what you would have, you would have the scattered pattern which is detected with the help of the hemispherical screen in this case, no. So what will happen, that the pattern which is there on the fluorescent screen, that will be like a fluorescent pattern, okay, and this pattern will be a reciprocal lattice pattern. So basically, reciprocal lattice is nothing but it is the diffracted lattice which gives you an image of the real lattice which is under consideration. What you are trying to do, that in this case you are having different lattice vectors which you can, of course, you can optimize. If you look into the these points, let's say that, okay, if you have k minus k naught is equal to g h k l. So what I'm writing here, okay, so here you have k is equal to, what is k is equal to 2 pi over lambda. Okay, what is k naught? K naught is the wave vector of the incident electrons, and k is the wave vector of the scattered electrons. So what you would have, 2 pi over lambda naught. Okay? Lambda naught. So what will happen with the help of this one? What is this GHKL? What is this GHKL in this case? You would have this GHKL, which is the, let's say that trying to make it a bit clear, like you would have H A star plus K B star, okay, plus L, you would have C star. So what you would have, that if you would like to look into the LEED pattern, basically it would be a diffraction pattern. And diffraction pattern means that we are talking about the reciprocal lattice in this case. And if you are talking about the reciprocal lattice, then how to understand this reciprocal lattice, that would be our understanding. Then how to get into the details of this reciprocal lattice. So what we have done so far, that we are trying to understand it with the help of this one. Okay? If you recall our setup, if you would like to have this information, again I am coming to this point. What you would have here from this setup, the things, first thing which we are giving in the equation is with the help of this, the electron gun. So don't confuse it, okay, because this fluorescent screen and these grids, they, the incident electrons, they are not affected with these fluorescent screen and the grids which are there. The setup is like that, no? So the electrons will go from here, okay? And when the only point is that when you would have the diffracted electron, they will be coming, okay? along with the diffracted electrons, you would have many other electrons like the inelastically scattered electrons. So what you would have when they will reach, they will be filtered out with the help of the grid number 1 and grid number 2, and only the scattered electrons which are satisfying the Bragg's law, 2d sine theta is equal to n lambda, they will be interfering constructively onto the fluorescent screen. Once they interfere on the fluorescent screen, now the screen is ready to have tell us that what is the if for example if it is a single crystal, then what is the lattice, how does it look like, okay, that information. And that was a viewpoint, means that okay, we can look at this point, you can also look from this point, you can also have a viewpoint here, and if you need to have any external detector, you can use this external detector for the detection of the additional events which are there, okay. So let's see that, okay, what we have done in this case, that first of all, the penetration depth which we are talking about, that is about the sample, okay. So if you look into the details of this penetration depth, then this penetration depth is quite small in this case, no? So you don't have very large penetration in this case. So if you look into the details here, so you would have the information about this. So you would have about this penetration about, let's say that in this case it would be like 4 to 10 angstrom, okay. So you see that, okay, only the surface which you are probing here in this case is that you are just having this knowledge about this, the surface of the order of this one, okay, 4 to 10 angstrom. So you are pretty on the surface in this case, what is the information which is coming from the surface. And second thing is that, okay, most of the information which is given in this case, that will be given with the help of this d, which is 4 into 10 4 to 10 angstrom in this case. So what is the order of this d, that is 4 to 10 angstrom in this case, no, okay. And now what we would like to understand from here, that we are trying to make it clear that this d is the penetration depth. This will tell us that how much depth is penetrated by the electron, and this is the mean free path of the electron, incident energy of the electron beam, and then what are the other processes, okay. So now what your sample is being hit by the electrons, what else would be done in this case, okay. Now one is, okay, one, the situation which you are looking at the fluorescent screen, that is quite obvious, okay. So that is you are getting the refined output from this screen. But on the other hand, you have the many processes which are going into the surface of the sample, which you cannot ignore. And these are like your phonon, like what are the phonon? Phonons are the quanta of the lattice vibration. So what you would have, basically the incident energy can be lost in terms of the heat, and which can come in terms of the phonons, okay, it can lose, okay. Then you can have the interaction of the electron and phonon. You can also have the interaction of the electron and electron, okay. These type of the events which you would have. And then what you would have, for example, if any of the electron which is scattered during this process, and the collective excitation which are there, that has to be taken into account while we are looking at the diffraction pattern which is coming onto the surface of the fluorescent screen, okay. So now lambda is equal to this one. So this is the standard pattern which we have, h is equal to 2me, and lambda is equal to 1 by 5, and this is approximate which we have approximation which we have done in this case. So this is like if you have what is the accelerating voltage in this case, that will decide the value of lambda, okay. And now we are coming to the this reciprocal lattice. Why we are interested about the reciprocal lattice in this case? Because we came for the electron diffraction, and remember that this diffraction is not X-ray diffraction, this is the electron diffraction. So what you have to look into, that you have to look, although the treatment remains same, because what you are treating in this case, in case of the diffraction, you are treating the incident radiation as the waves. Okay, what you would have the if you know the general and the detailed theory of this X-ray diffraction, that how does it work, you will be automatically be able to know about this the electron diffraction also. Okay, so what you are trying to do here, you have these are the primitive vectors A, B, C, let's say for the cubic cell. And then what if you would like to look at what would be the reciprocal lattice vector of the A, then that is denoted with the help of this A star and B star, and then this is C star. These are the, now you would have a reciprocal space. Okay, instead of having a real space, you would have a reciprocal space, and where this space would be, this would be on your fluorescent screen which you are looking at. Okay, in case of the LEED pattern. Okay. Now when you are looking at this fluorescent screen, you would have that diffracted pattern which is going to give you the information about the single crystal which you are trying to probe in this case. So there are two things which we would like to understand here. Okay, if you have the knowledge of the incident wave vector and the scattered wave vector, you would have this GHKL. Okay, so you would have this GHKL, and then you can write that in terms of HKL vectors. Okay, in this case. So if you look into the this the this GHKL, you would have that information about all the information about the system which is given in this case. Okay, so basically you are trying to understand that the GHKL giving you the details of the reciprocal lattice. Okay, so basically it is the reciprocal lattice vector which is coming into play in this case. Okay, so GHKL is the reciprocal lattice vector in this case, and A star, B star are the primitive cells in the reciprocal space in this case. No? Yeah, do not hesitate to ask me questions, and I would give you a small exercise for your next lecture. Okay, so can you have a look at this term which is known as the evolved sphere? Okay, can you have a look at this, and then we can have a discussion about this evolved sphere in our next lecture. Okay? Please don't hesitate to ask me questions if you have any question. Yeah, I'm enabling your voice. Yes, please don't hesitate to ask me any questions. If you have any questions, please don't hesitate to ask me any question. Yes. And Jasprit, are you there?
Yes, sir.
Yeah, so what we are thinking that try to understand the experimental configuration of this frog setup, and once you get this experimental configuration, after that we can organize your presentation, the dissertation student presentation, both for you and Pavanjot, and then we can discuss it. Okay. Okay. So look at you are telling that there are different type of the frog setups, but yeah, whenever you are talking about that, tell me the information from where you are reading it. Share that paper with me so that I can give you more advice. Otherwise, I don't know what you are talking about. So look at these setup. Experimental configuration should be your priority. That look at that experimental configuration, and that would be helpful for you. So basically, if you would like to measure the temporal profile of the pulses, you can do that with the help of the frog setup in this case. Is it clear, Jasprit? Yeah, ask me question if you have. Jasprit, you want to say something?
हेलो सर, वो नेटवर्क इशू हो गया, पता नहीं लगा.
Yeah, so आपका network issue is a big problem because every time whenever there is a decisive work
Yes.
and look for
Yes,
good
sir.
network.
Yes,
Yeah,
sir.
so everyday problem. So
Sir,
we have to find out some
sir
solution for that.
रिपीट करना
Yes,
आपने क्या बोला था?
yeah, I'm just saying that, okay, try to look at the experimental configuration from which paper you are talking about and tell me that paper. Okay,
Sir,
share that paper with me, and then when you share that paper, I can give you more advice. Okay. In the
okay, sir.
meantime,
Okay,
look at the
okay, sir.
frog setup, which is the frog setup over there. Look at what is the aim of this setup, which is to find out the temporal profile of the pulse, and then we
Okay,
can
sir.
have the presentation of yours, and then we can discuss more. Okay. So you
Okay,
have
sir.
to
Okay.
invite discussions. Okay. In case of the
Okay, sir.
dissertation, you show some progress, and we would take that progress ahead.
Okay, sir.
Okay. I'm leaving the
Okay,
session.
thanks.